Welcome back to another video on the course on probability theory. Last time we discussed connections between convergence in probability and almost true convergence. And this time we'll turn to a different pair of kinds of convergence, which are convergence in probability and LP convergence. On our way, we will have something which is called uniform integrability, which connects also our findings here to the theorem of dominated convergence. Let's see what that means. Okay, LP convergence and convergence in probability, which means this right-hand side of this figure. As you can see here, so what should we prove today? LP convergence implies convergence in probability. That will not be hard. On the other hand, if you have something which converges in probability and you need that it converges in LP, then you need something called here uniform integrability. And well, let's see what it is actually. So it's defined here. It's an expectation of x over a set such that xi is bigger than k, sup over I, inf over k. So I can also put that differently. If for all epsilon bigger than 0, there exists a k less than infinity such that the expectation, which is written down here, is smaller than epsilon, then it's uniformly integrable. Because, well, if for all epsilon I find this k here, that's smaller than epsilon for all for all I in I. So if this here is smaller than epsilon for all I in I, then the supremum here is smaller than epsilon. And if I then take the infimum over all k, which means I need a big K, I can bring that always to something apparently bigger than any epsilon, then this here just goes down to 0. So that's just formally equivalent, so no big deal. But what does that mean? It's a bit hard to draw this in some sense, but let me try. So, I mean, it's a bit odd to say, well, that's omega, okay. And here I have real valued random numbers, so xi. So maybe something like this here. Oops, that's my xi. And my k is here. And this integral here, what does that mean? That means, let me take a different color. This here. I'm integrating over the function which is xi on the set that xi is bigger than k and 0 otherwise, which means I'm computing this area under this curve here. This here is left aside. Okay, so let's start with a counterexample. A counterexample in the sense that I really need this uniform integrability, because if I have convergence in probability, there is a chance that the sequence does not converge in LP, and we already had something like this. So U is uniformly distributed on 0, 1. If it's in 0 to 1 over n, the yn is n, like this here. Otherwise it's 0, which means, for example, the expectation of epsilon n is n times the probability, exactly, it's n times the probability that I'm in Bn, which is 1 over n, which is 1. So the expectation of yn is 1. However, I have almost sure convergence to 0, which also means I have convergence in probability to 0. So the probability in black, the probability that yn goes to 0, well, when does yn go to 0? Always if u is not 0, because if u is not 0, it's some positive number. And if it's some positive number, there will be an n such that yn is never in Bn. And this is 1, of course. Okay, on the other hand, I do not have convergence in L1, as we already said, because then we should have the expectation of yn minus 0, which would be the limit. That's the expectation of yn. And we just said this is 1, because this is sorry, that's that's n times the probability that u in Bn, and this is 1. So I have yn converges almost surely to y equals 0. But yn does not converge in L1 to 0. That does not hold. And we are going to show that for this direction here, we need uniform integrability. This can only hold if that sequence which we just had here is not uniformly integrable. Oops. And it's not, because when I write that down, inf over all k, sup over all n, expectation of yn over the set yn is bigger than k. The set yn bigger than k, that's the set, well, at most un u in Bn, but if u is not in Bn, then yn is 0 anyway, which means that the whole expectation here is the same as the expectation of yn. And then we had this is 1. But if it would be uniformly integrable, it should be 0, what comes out here. So that's not true, so it's not uniformly integrable. Okay. Some more examples about uniform integrability. First of all, I have a family which is bounded by some integrable random variable. Then I claim yi is uniformly integrable, because just by definition, if I have the sup over all I expectation xi over the set xi bigger than k, I claim this here is smaller or equal as y over the set y bigger than k, because xi is smaller than y, and if xi is bigger than k, y is also bigger than k. So that is true here. And this here, a claim for k goes to infinity, goes to 0. And the reason is, as almost always in this lecture, the theorem of dominated convergence. Y times this indicator y bigger than k goes to 0 almost surely as k goes to infinity, because y is real valued. And y is integrable, which means that the probability that y equals infinity is 0. So this here goes to 0. This here goes to 0 almost surely. And it has a dominated function, which is y. It's in L1 here, which means I can interchange limit and expectation. So the limit of this here, as k goes to infinity, must be 0. Okay. Then next example. If I is finite, and xi in L1, then xi I in I, so it must be in L1 for all I, of course. Xi I in I is uniformly integrable, I claim. And the reason is, well, I can define S as the sum over the absolute values of I in I. This is in L1. This is in L1, and it's also dominating all xi's. So what I have here is already the assumptions of the first example here. That means, so these here are uniformly integrable. That was easy. Then another very important example, if xi is for all I in some LP for p bigger than 1, and the supremum of the expectation xi to the power of p is finite. So for example, if p equals 2 means that the second moments are bounded, then I have that the xi's by themselves are uniformly integrable. Xi I in I uniformly integrable. And the reason is, well, let me just write down the definition. Sup over all I, expectation of absolute value xi over the set absolute value of I bigger than k. I will bound this, and I will first write it down. Sup over all I, expectation xi to the power of p divided by k to the p minus 1. And why is this inequality true here? It's true, for example, multiply both sides by k to the power of p minus 1. K to the power of p minus 1 times absolute value of xi on this set here is smaller than xi to the power of p, because xi is bigger than k. Yeah, so on this set it's okay, and also on the other set it's clear anyway, because if xi is more than k, I have a 0 here and something non-negative here, so that's clear anyway. And here on the right hand side we have this here is finite, that's bounded from above by this supremum here. And if k goes to infinity, it has to go down to 0 on the right hand side. So much for the examples, and now I come to a main result. Equivalent formulations for uniform integrability. Here you also learn a little bit better how to imagine uniform integrability. We will need the fourth thing quite often. So let me just start with the fourth thing, which is also connected to the third example from the last slide. So here we had something like this here. supremum of expectation of some moment bigger than 1 is finite. And as it turns out, it's equivalent, uniform integrability, and something similar than this here, but the expectation over f of absolute value of xi, and the f has to be non-negative, and fx divided by x has to go to infinity. In proofs, we will also have that the second thing is equivalent, so expectations are bounded. And, well, that sounds complicated here. So you make a soup over all I. Okay, we had that. You make a soup over all sets which have measure less than epsilon here in the back. And then you also take an epsilon going down to 0. Yeah, and then you have to have 0 in order for xi, the family xi, to be uniformly integrable. And the third one we more or less only need in order to construct the fourth one. Okay, so let's get started. Let's prove from 1 we have 2. So first of all, choose delta and k such that, because we have a uniformly integrable family, soup over all I expectation xi over the set xi bigger than k is smaller than delta, maybe equal. And then we need to prove these two things here, and we do that in basically one step. Let me write down the expectation of absolute value xi over some set A, which is of course in the set of measurable sets. I can say, well, xi over the set A intersected with xi bigger than k bigger than k, like this here, plus, and then the same thing with smaller or equal than k. Okay. Then we have this here is smaller than delta. So bounded from above, we have this here is more equal to delta. And the last bit here, so that's the same with the smaller equal sign here. So on this set here, xi is bounded by k apparently, plus k times the probability of the set here. So probability of A intersect with something, that's bounded from above by P of A. And this here, because A is just a set, P of A is smaller than 1. I mean, just leave it like this. We need here two things. So this here should be finite. So in the first thing here, we can achieve this by taking A equals the whole space. A is omega, but then we still have small equal than delta plus k. In particular, that's finite. And for the second one, we take, well, epsilon going to 0, and the worst A such that P of A is smaller than epsilon, which means we have here P of A is smaller than epsilon. And the supreme over all xa. Okay, we have this here. but we can bound from above this thing here by delta plus k times epsilon. And then going down to 0 means we have something small or equal to delta. But that's okay because delta was chosen arbitrary. And that's how we show from 1 follows 2. Okay. Then next step, if I have 2, I want to have 3. Here again we have to bound something. Xi minus k, and the positive part is smaller or equal. I claim then absolute value of xi times the indicator that xi is bigger or equal than k. Because, well, if xi is bigger, then this here still subtracts something, but it doesn't. And if xi is smaller than k, here's the 0 and here's the 0. So that's okay. So I want to show the third part, and we have that this expectation here is small or equal than expectation of xi times the probability that xi is bigger than k. So what do we need? Sup over all I expectation. Absolute value of xi minus k plus is smaller or equal than something. Okay, I need something else. I need some k with the property that the absolute value of xi smaller than k epsilon is smaller than epsilon. I can have this because the first thing here applies. So that means that cannot have, well, this here uniformly goes to 0 by, for example, Chebyshev inequality. So I have this k epsilon here with this property. And that means if I take a limit, k goes to infinity, that's, well, the same limit as saying epsilon goes to 0. Sup over all I expectation xi minus k epsilon plus. Then I can use what I had before, which is this inequality here. The expectation, I need the limit and the sup. Limit epsilon goes to 0, sup over all I expectation xi absolute value over this set here, xi bigger than k. So this set here, as you see, has probability at most epsilon. I know that 2 applies here and this here. If I plug in here the supremum over all these i's, I make all this thing here bigger. And then I know this here converges to 0. So that means this here must be 0. And we have shown the third part. Okay, let's come to another one. So the fourth. So from 3 we also have 4. Here I say let K1, K2 and so on be increasing to infinity with the property that the expectation of xn minus kn plus is smaller or less than 2 to the minus n, which is a summable thing, which we will need in a second. Okay, 3 applies, so I take the kn's such that this here is the sequence converging to 0 as fast as I like, essentially. Then I can define my f of x equals a sum k from 1 to infinity, x minus kn plus this positive part. You see all these functions here are monotonally increasing in k. They are also convex in k. That means since sums of increasing functions are increasing and sums of convex functions are convex, monotone increasing and convex. And I also need a property, which is if x is bigger or equal than 2kn, then I claim f of x divided by x is bigger or equal than the sum k from 1 to n, 1 minus k divided by x, bigger or equal to n over 2. So why is that? For the first inequality here, multiply both with x. So I claim f of x is bigger or equal than the sum x minus k. And this is true because f of x is defined as the sum here of the positive parts, which all are bigger than x minus kk themselves, which proves the first thing here. And for the second thing, remember that x is bigger than 2kn here. So 1 minus kk over x wait. So how does this work here? If x is bigger than 2kn, then I have, since the kns are increasing, okay, yeah, x is bigger than this here, kn is increasing, which means, okay, these here, kk divided by x kk is increasing, which means all these here are bigger than a half. All of these sums are bigger than a half because kk divided by x is smaller or equal than a half. Okay, like this here. And all the sums here are bigger than a half. N of them have bigger or equal than n half. Okay. Which means that ff over x here converges to infinity if x is allowed to converge to infinity. So that's this property here. Ff over x goes to infinity. And I need also here that the supremum here has to be finite. Let's compute this. expectation of absolute value f of x, no, f of absolute value I want to say, f of absolute value of xi, well, f is a sum, k from 1 to infinity, absolute value of xi minus kn plus, which is smaller or equal than sum over 2 to the minus n, which is 1, because we have chosen it like this here. Kn's we've just chosen like this. Okay, and then we still require the last bit from 4 back to 1. And then we have all the characterization here. From 4 to 1 we still need. Define. AK is the infimum, x bigger than k, f of x divided by x. This here means this here converges to infinity by assumption. F of x divided by x converges to infinity. We need to show uniform integrability, which means we have to deal with the supreme over all I, expectation of absolute value of xi over the set absolute value of xi bigger than k. We need to let k goes to infinity then. I claim this here. I can bound from above by saying 1 over ak supremum over all I, expectation of f of absolute value of xi over the set xi bigger than k. Why is that? So ak is this infimum. Here the xi is bigger than k, so this here applies. So ak is smaller than f of xi divided by xi, which I can also say, well, xi is smaller than f of xi divided by ak, just by rearranging this here. And this is what happened. Xi is smaller than f of xi divided by ak, like this. This here is bounded from above by 1 over ak supremum over oi, expectation of f of absolute value of xi, so just ignoring this restriction here. And this here already goes to 0 as k goes to infinity, because this here is bounded, and this set here goes down to 0 anyway. So 1 over ak goes down to 0 because ak goes to infinity by assumption. Okay, great. And I forgot one thing. The f here in 4 can be chosen to be increasing and convex, because the thing we defined here is increasing and convex. So assume this here does not imply, so this here holds for, okay, this here has to hold, but f is not increasing and not convex. From this we have just shown, for example, it's uniform integrable. From this you can show, well, this f here also applies, and this is then uniformly is then monetarily increasing and convex. So that's this thing here. Then some more lemmas or examples or so, which we will need in the future now. This here I can be brief, I guess. So xi to the power of p is uniformly integrable if and only if for some or for any x in LP with p not less than 1, the sum of xi and x is uniformly integrable. And the proof is really simple because, well, by the Minkowski inequality, you can plug apart xi plus x, its absolute value, and absolute value of x here, an absolute value of xi to the power of p. And this here is finite. And here you have to be a bit more careful, but not really, because the same thing applies. Yeah. So xi minus x to the power of p, I can bound from above by the absolute value of xi and the absolute value of x, which then goes to 0. And we have shown this. Of course, that was only one part, but the other part is the same because from this here I can just add minus x and I'm here. So it only requires to prove from left to right. Then we have what we wanted to have, as we have here convergence probability and LP convergence. So we already saw on the first slide they're connected in the sense, well, if convergence in LP, then I have convergence in probability and uniform integrability. So that's this main result here. And there are two directions now. And one part we already have, I think. No. Not really. I mean, we had that LP convergence implies convergence in probability. That's just Chebyshev's inequality, but nothing else. So, for example, from right to left. So no convergence in probability and uniform integrability. So for this weak limit here, not weak limit, limit probability here, I can use Fatou's lemma, expectation of lim inf xnk to the power of p. And here k to infinity. So that works for any subsequence. This is smaller or equal than. Here's Fatou's lemma. Here now comes Fatou's lemma, and xnk is just some subsequence. Then expectation of supremum or supremum of the expectations. Xnk to the power of p, which is finite by assumption. Because the x and p's are uniformly integrable. We know this. In addition, what else do we need? Okay, we need to show convergence in LP convergence. We need to prove. So xn minus x to the power of p. This here has to go down to 0, and I can bound it by xn minus x to the power of p on the set xn minus x bigger than delta, plus the same thing here, on the set x minus x smaller or equal than delta, but this is bound from above by saying, well, minimum 1. Because, yeah, here I have the border at 1. Then this here converges to 0 because I can assume convergence in probability. And this here I can assume also convergence to 0 because this here goes to 0 and I have uniform integrability. So by this, the first term goes to 0, and by convergence probability the second goes to 0, which means if n goes to infinity, this here has to go down to infinity. Down to 0, of course. And we have shown from right to left. And we have also shown here, that was the first thing, x has to be in LP, and it is in LP as we show here. But from left to right, I would have to have started with this, from left to right, let's do it now. First I have to show convergence in probability. That is the simple part, xn minus x bigger than epsilon, smaller or equal than the expectation of xn minus x to the power of p divided by epsilon to the power of p, which as n goes to infinity down to 0 because the numerator does this. And we have shown convergence in probability. So that was an easy step. But we still have to show that xn minus x to the power of p, n, 1, 2, and so on, that they are uniformly integrable. The difference here is, well, I would have to show xn is uniformly integrable, but I'm showing xn minus x uniformly integrable. But from x, I already know by assumption it's in LP. By this one example here, well, you can add functions. Okay, it's in LP now, as it's required here. And you have uniform integrability of this here, exactly if and only if xi to the p is uniformly integrable, and that's what I'm doing here. So I've shown this here, I'm adding x, it's still uniformly integrable, and I only need this here. And how do I do this? I'm going to take the second property here. Well, suprema over expectations have to be finite, and this here also holds. So expectation of xn minus x to the power of p sup over all n, that converges to 0 by assumption, because xn goes to x. So this here is finite, of course, because that sequence goes to 0. So it's finite, that's the first step. And the second step, I have to compute the supreme over all a, p of a smaller than epsilon, sup over all n, the expectation over all xn minus x over the set A, and epsilon's going down to 0 as well in this computation. But let's just try to bound this from above. Yeah. How does this work? So there are two steps we need here. First, take a big N such that supremum over n bigger than big N, expectation xn minus x to the power of p is smaller than some delta which I had before. So take delta bigger than 0, and this here we take the n such that this here is smaller than delta. That works because this here converges down to 0 anyway. Plus sup a p of a smaller than epsilon, sup n from 1 to capital N, expectation, what we have here, just writing it down, xn minus x over a plus this here. So what I'm doing here, essentially, okay, bounding from above. So I'm splitting this supremum here in all n bigger than n. For n bigger than n, I just delete the a here. And for smaller than n, I keep it. But I can do it like this. I can first choose my n. Then I write it like this here. This here, as epsilon goes down to 0. So as epsilon goes down to 0, converges to something smaller than delta, exactly to this thing here, because this here converges down to 0, because this here is a finite family. So delta was arbitrary. It converges to something smaller than delta, which means it has to converge to 0. Right. And we are done. Okay, and then last slide for today. One more little thing, which is sometimes useful. Xn converges to x in LP. Then it's uniformly equal, and equivalent are, well, the expectations, so the pth moments converge. And this here is sometimes easily verified. It's easier to verify that the whole thing here is uniformly integrable. And I can assume here that I have a convergence in probability. And this here means 1 and 3 are equivalent. That's okay by the last theorem. Because the last theorem said that convergence in probability plus uniform integrability is the same as, well, convergence in LP. And then I show that from 1 I can conclude 2. This is easy because xn minus x is more equal than xn minus x. And well, I can also do the double things here. And p below here, so that still works because this here is just a norm over all intervals, and by assumption 1 holds, converges in LP. This here converges to 0. Converges to 0 as n goes to infinity. That's just a triangle inequality I need here. Exactly. And from 2 to 3, it's a bit more complicated. I have to show that the family xn to the power of p is uniformly integrable. And I write down the definition, expectation of xn to the power of p over the set xn bigger than k. And I do something which looks complicated. Expectation over xn to the power of p minus x. I think I better use a new line here. Expectation of xn to the power of p minus xn minimum k minus xn plus and this here to the power of p. Okay, let's check it. So this here, this function is xn to the power of k if xn is bigger than k. But if xn is bigger than k, this here is 0. The minimum is 0. And I also have xn to the power of k here, as I do here. On the set xn is smaller than k, this one here is 0. And here I subtract something which is smaller than xn from xn, which means the thing is always non-negative. So I've shown this less or equal. And here I have, if n goes to infinity, well, what can I conclude here? So I can use that this here converges. So this xn to the power of p converges to expectation of x to the power of p. In addition, I can use that the same thing holds here. Yeah, because xn converges to x in LP, as in probability. And I have also uniform integrability of the same thing here. So minus x minimum k minus x plus to the power of p. And now as k goes to infinity, well, if this here grows and grows, this here converges to x, because at some point k is bigger than x. K is bigger than x. And the minimum here is x itself. So and x minus x is equals 0. So that means here this one is going to be 0. And again here I need dominated convergence, because this here is the dominating function. Yeah, so x to the power of p dominates this here index with k. Okay, we've shown this equivalence here, and that means we are done for today. So we are done with basically, for the moment, this figure that we had. We essentially only proved the upper part here. The lower part will come later in the manuscript. And next time it's going to be about independent random variables. Okay, see you then.